Okay, so I see people are coming. Okay, so number of people are increasing. So let's wait 1 more minute and we start. Okay, well, so maybe we could start with this second talk of today's session. It's a pleasure to have Leni Bascones here on this conference. And so since 2009, she's tenured scientist at the Instituto de Ciencia de Materiales de Madrid. And she is a theorist. She works on modeling the electronic properties of, well, strongly correlated electron systems, such as superconductor or ITC superconductors, and more recently, that twisted bilayer graphene. So thanks, Lena, for being here, and floor is yours. Just one quick remark: if you have any question, use either raise your hand or question and answer, and then we'll take them in a chronological order. Thanks a lot.
Okay. So thanks. Well, I would like to start joining my colleagues, thanking the organizer for putting together this wonderful conference, and even adapting themselves to the complicated situation we are now internationally with the COVID. And also, I would like to thank them for inviting me to talk here. So I'm going to, well, as Antoine has said, I'm a theorist, and I will talk about the interactions in this twist bilayer graphene. Well, I think that after this week and, well, the excitement of these years, I don't have to justify why we are interested in really understanding these systems. So that in this particular this great phase diagram that Pablo discovered a couple of years ago, and that with many experiments have shown us that there are, well, the phase diagram is even more complex and is full of superconducting and correlated phases. There are many things that we don't know about the correlations into this bilayer graphene. We know that the correlations appear because at the magic angle we have flat bands. And at this point, we know that some symmetry breakings appear. You have seen now, for example, the talk by Moiré Wannier, but there have been several other experiments like this cascade of phase transitions that have shown us that different things happen, different phases are happening. Now, we don't know much on which is the nature of this symmetry breaking in particular, because it seems that there are sometimes even external facts like strain or alignment to boron nitride, which are affecting them, but also because it seems that in this system, at least according to what we heard last week in several talks, both in Alan's talk, in Paco Guinea's talk, and in Ashwin Vishwanath's talk, so it seems that the different in energies for different symmetry breaking states are very small. For some of us, there is a fundamental question which has to be answered, and is whether mode physics is involved in these systems, or whether the symmetry breakings which appear are just standard mean field symmetry breaking. This question is important, first because mode physics is fascinating, but also overall because mode correlations are an important part of the properties of other correlated superconductors, of course of the cuprates, but also of the iron superconductors, of the heavy fermions, and other systems like organic compounds. So the easiest way to understand mode physics is from the Hubbard model in a single orbital. So in this system, imagine that we have just an atomic system. So well, let's say a lattice of atoms with a single orbital. And so our electrons can hop. So we have some energy T. But that there is, if we find two electrons in the same side, they interact and they discuss energy. So then if the electrons hop, at some point there is, the hope involves, so goes to an orbital in which there is already one electron, there will be an interplay on whether the energy saved by hopping is larger or smaller than the energy which caused the double occupancy. And in particular, if this interaction is much larger than this hopping, so then the kinetic energy, the hopping, will not happen. So you can be here, you can easily realize here that what is going to control whether this hopping is forbidden is the relation between the kinetic energy, the bandwidth, and this interaction U. If the system is, has a filling which is at integer fillings, then for large interactions, we can even go to an insulating state, to a mode insulator. And in particular, you can realize that here I haven't rely on symmetry breaking, and in fact, mode insulators do not require symmetry breaking, even if most of the time they have, we are going to find that they order in some way. In the twist bilayer graphene, for our atoms or our lattice sites, we're going to think in general in these unit cells, in all the Moiré unit cells. So we don't have to think on the carbon atoms, but it will be on the all the Moiré unit cell. A characteristic of the mode physics is the transfers of a spectral wave. In particular, we can see two examples. If we are in a non-interacting system, we have a description. Our band is what we are used to. These are our spin degenerate quasi-particle bands, well-defined in K-space. If we are in the mode insulating state, what we have is that all the spectral wave has been transferred to the many-body Hubbard bands. So these are not quasi-particle bands, but these are bands of singly occupied or doubly occupied states, at least, well, the simple thing is if we are in the single orbital Hubbard model. Now, in between, there are situations in which we can have a metallic state, a correlated metal, in which there is quasi-particle band, part of the spectral wave is in the quasi-particle band and part is in the Hubbard bands. So most of the studies that have been done in twist bilayer graphene, and in particular the ones that we heard last week, have been done, are based on Hartree in the continuum model, which is a model defined in K-space. And so in these works, in fact, what this has been studied is mostly whether a gap opens in this quasi-particle band. Now, but in fact, for example, as Ali Jatani was saying the other day, so the question is whether there is this mode physics, and in particular, for example, what he was saying is that the spectra that he sees cannot be explained with just standard symmetry breaking in the quasi-particle band. So if we want to study mode physics, besides some specific techniques which are able to deal with these many-body correlations associated to mode, something that we are interested in is having interactive models which are based on effective barrier function. I mean, a way in which we can really, instead of working in this continuum or on atomic orbitals based on carbon, working on effective barrier functions for all the Moiré. Something like seeing our Moiré unit cell as atoms having the less number of possible effective barrier functions. This, of course, is also going to study it's also going to allow to study symmetry breakings and even may facilitate to get inside. But this is going to be especially important for mod physics. So, well, this talk is going to be about interactions in between these effective barrier functions and how we expect them to be. But before, I want to remind some effect that was also discussed last week, because it's going to appear later in the talk. So we have seen also before this picture in the previous talk. In particular, so we can see when there is this twisting of the layers, when there are the two layers. So there are these regions are formed, the AA region here, and the B and BA regions here on the border of this unit cell. If we start doping the twist bilayer, what we expect is that the electrons, so in this region of space, so in this region of dopings, are going to the AA region. And so this is going to create a charge modulation within a unit cell. It was early recognized by Rademacher and Mellado and by Guinea and Ballet that at gamma, the electronic states are not at the AA region. And so when doping the system due to the interaction, two effects were expected to appear. On one side, there was expected a strong modification of the electronic bands with doping. And on the other side, some charge redistribution away from AA was, from the AA region was expected to happen. And in fact, so these are the kind of effect, which in fact is a very strong effect that Paco showed the other day. You can see this is the, if this is the undoped band for some value of the screening factor. So he saw that if he doped with one electron, he expects to change the band by in this amount to this other shape. Well, if he dopes with one hole, it will have a completely different effect. But also, in fact, it has a very large magnitude. This effect also appear in Alan McDonald's talk, and also Marco Pollini discussed that. So this will appear later. Just want to remind you. Okay, so let's go back now to our Moiré functions. As I said, we would like to have some kind of effective orbitals for the Moiré. And of course, we would like to have the minimum number that we can. So having this in mind, so people already started, started early doing this, building these models for the Moiré. And at the beginning, in this idea of trying to have the simplest models as possible, it was only the two flat bands were fitted, and models with two orbitals per valley were built. This gave rise to a very peculiar barrier functions, the famous spinner functions, in which even if we expect to have, and we will have, the charge concentrated at the AA region, the barrier function is centered at the BA region. So somehow, even if the barrier function is centered here, it will have charge here, here, and here. So from the very beginning, there were different groups, including Ashwin Vishwanath, Senthil, and Trey Bernabik, raised some issues with the symmetry and the topology that's were partially discussed, were mostly discussed last week, and which I will not go through. But from the point of view of the correlations, these Wannier functions are also a bit special and I will say inconvenient, in the sense that this overlap that the overlap. So let's say you see we will have one Wannier function here and another function centered here. The lobes of the two Wannier functions are going to overlap strongly. So, and this gives rise to extremely long-range interactions, to large chains, and also to assisted hopping. So in particular, you can see here, for example, these are the density-density interactions between the Wannier functions. You can see these are Wannier functions on the same side. This is what normally one calls the Hubbard interaction. But if you see the interaction to first nearest neighbor, second, third, you see that it really decays in very, very, very slowly. We see that there are also largest change, but, and in principle, people thought, okay, this is just a ferromagnetic state, what we get. But then, well, from the work by Oscar Buffett, so it was seen that, in fact, the assisted hopping terms also affected the ground state as to compensate this exchange. And in particular, so this assisted hopping were shown by Paco-Guinea to be necessary to explain this very strong effect that it shows up in the Hartree level of the continuum model. So mostly due to these symmetry issues, different authors propose other models, so models for the Moiré Wannier functions, which instead having 2 orbitals per valley, they had more orbitals per valley. So in particular, there has been models proposed with 4, 5, 6, 8, and 10 orbitals per valley. For all these models, the one that, in my opinion, is the most suitable is this 8-band model that it was recently proposed by the Harvard group, particularly by Stephen Carr, Chimos Casiras, Ashwin Viswanathan and colleagues. Now, they propose the Wannier functions, but if we want to work with these models, and if we want to study the correlations, we also need to know how these Wannier functions interact. And so this is what we have studied. We have studied how the electrons, which are in this Moiré Wannier function of this 8-orbital model, interact. And so this will help us to study then the correlations. So this is the outline that I'm going to follow now. So after this introduction, I will introduce this effective 8-orbital model that it was proposed by Stephen Carr and colleagues, and then we will see how are the interactions in this model. I will first talk about the density-density interactions. In particular, we will see how this is intraorbital and interorbital interactions. So how large are these interactions in the absence of the gate? Then we will see the effect of a gate, and we will see what happens when we go to the Hartree approximation. We will see that we learn some things, and later I will see how are the other interaction terms in this model. So these, in fact, what it will give us is the interacting Hamiltonian to look at these systems. Okay, so let's go now with this 8-orbital model. So what Stephen Carr and colleagues did, so well, they first studied the band structure of a relaxed TVG. So there is no reason that the Wannier function has to be only for the relaxed band structure. So it can be also calculated for a non-relaxed system. But in fact, the results that I'm going to describe are for a relaxed system. So, well, they calculated that, and they in fact derive also an effective KP model. And then what they are doing is they are fitting the band structure first the flat bands and also the closest band, but not necessarily at the largest energies, not necessarily the closest bands. You can see here how well this model works in this range of angles. So it's not a model that is expected to work for any angle, but you can see here that in this range of angles, which is the validity of the model, it goes very well, and it keeps not only the different energies that of course are also associated with fitting parameters, but all the crossings. Now, before when I have described the two orbital model, I have mentioned that the Wannier function of the two orbital model were placed here at these AB and BA regions, even if the charge was expected to be here at the AA. In fact, well, in the Moiré, we can describe three different lattices. One is the triangular lattice, which is defined by this by the AA center. There is also the honeycomb lattice defined by the AB and BA regions, and also we can define what is sometimes called, well, domain walls or associated to the domain walls, or the saddle points, which are in between these AA points, or the middle points, which are or in between these AB, BA points. And these points form a Kagome lattice. Well, this model, this 8-orbital model, includes Wannier functions, which are centered at the three lattices. You can see here how this is our unit cell and how the orbitals are centered. So in general, I'm going to try to follow a color code, which is it's purple for the for this DW, for this Kagome lattice, green for the honeycomb lattice, and then, well, for this triangular lattice, it will be mostly orange, but sometimes it's going to be red, just because there are two different kind of orbitals. Okay, so well, in general, we talk about an 8-orbital model per valley, but an 8-orbital model in general, but now keep in mind that there is valley degeneracy. So in reality, what we have is 16 orbitals, so 16 spin degenerate orbitals. And so all these electrons, all these orbitals are going to be involved in the interactions. So for the band structure, so it's assumed valley conservation, and then it's enough to define the orbitals in one of the valleys, because the orbitals in the other valley are related by time reversal symmetry. So now for the, in this model, I have told you that we have electrons in the different lattices. So in particular, we have, in this triangular lattice, we have two kinds of electrons here at the AA centers. And in particular, we have AAP orbitals. We have one P plus and we have P minus orbital in each valley. So this means that here at the AA center, we have 4 AAP orbitals, and also here at the AA center, in each valley, we are going to have 1 S orbital. Okay, so in total, we have at this AA region, we are going to have in total 6 orbitals. At this honeycomb lattice, we are going to have 4 orbitals in total. Here the symmetry is PC, and at the Kagome lattice, we also have 6 orbitals, and it's S symmetry. So many of you may be more familiar with the previous 10 orbital model that it was proposed by Senthil Choudhury and Ashwin Vishwanath. So there are many analogies between these two models. And of course, the number of orbitals is different, also a bit the symmetry. And something also important is this model, is that this model is based on the Wannier functions. So you can see here the orbital dependent, the composition of the bands. And what emerges clearly from the very beginning is that most of the spectral weight of the bands, in particular more of the 90%, is associated to a particular kind of orbital, in particular to the AAP orbitals. You can see them here. And you can see how here, this is the AA region, how the charge is centered at these AA regions for both of them. So then this is in fact the region where we have said that we expect to have the charge when we dock the system. Because we have the two valleys, so we can have 4 degenerate p orbitals at AA that will be able to hold up to 8 electrons. So it is clear that these orbitals are going to play a prominent role in the physics of the twist bilayer graphene. However, something important that will in fact show up later is that here at the gamma point, the symmetry of the bands is different. In particular, one of the bands have PC symmetry and the other one have S symmetry, okay? You remember before we said that at the gamma point, so the electrons were not centered just right at AA. Okay, so this is our model. And in particular, this we see that we have these 4 degenerate orbitals that will accommodate up to 8 electrons, which are going to play a prominent role. But we want to see how all these orbitals interact and how they interact not only among them and also with the other ones. And this is in fact what we have calculated in our work that will be posted in a few days in Hund. Okay, so let's now go to the introduction and let's now see what conclusions we can expect for our system. So if I don't see anything, I'm going to use an interaction potential for the carbon atoms that goes like 1/r. And here, an important aspect, it's this screening constant. In general, we don't know if which is the value of the screening constant. So whenever you see any prediction by a theorist, be aware that they are going to be using a particular value, and that this can influence, of course, the interactions. Okay, so here it's clear that it goes like 1/epsilon. So if we change the value, for example, if we make epsilon smaller, the interaction that I'm going to use are going to be larger. But it's just trivial to go through the value. So that just don't try to believe too much any exact value. Okay, so the very first thing that it appears here, these are the intraorbital interaction. So this is telling us a bit what is normally called the Hubbard interaction for each orbital. So in fact, is the interaction which experience the electrons which are at a particular, let's call it, well, atom and an orbital, atom, like effective atom. And the very first thing that we see is that the on-site interaction for these AAP orbitals is much larger than the other ones, of the order of a factor 2. In fact, this is not surprising if one looks at the average radius. So these orbitals here that we have seen, this AAP that we have seen that are going to be our main players, have a much smaller radius than the other ones. So the interactions are not exactly given by the radius, but because also the shape and the interaction is important. But so this can give us more or less an idea of the value. So in fact, if we try to, if we take this quantity, this on-site interaction, and try to compare with some effective distance, which appears some effective width, we see this radius that will appear here is around 28 angstroms, so only 2.8 nanometers. Now, the other thing that we can see here is that, well, even if this energy dominates, so these other interaction energies are not so small. So the question is what kind of role can they play, how much we should care about them. So here we go back to the orbital dependent bands. And in particular, we can see that while these ones are very local and in energy, so the band looks thin, so the orbital weight of these other orbitals seems spread on a much larger range of energies. So you can see this in the orbital result laws, density of states. So we see that the bandwidths of the AAP, this I'm going to call them flat bands to make them easier to identify. So we see that it's very flat. So it's of the order of 20, 30 milli-electron volts. So it's smaller than the interaction. So then we can expect that most probably in this system, we are going to find for these orbitals mode physics. Now, if we look at the other orbitals, the bandwidth is much wider, and it extends over, let's say, 200 or 300. So most probably at these angles, from the point of view of mode, we will not find them correlated. But of course, many of you are probably looking at this big peak in the density of states, so that they are most probably not correlated in the mode sense does not mean that we will not find any other kind of instabilities, so that we can find them. And in particular, so this system, this orbital becomes more interesting even more interesting as we decrease the angle. We have seen before that if we decrease the angle, the bands become narrower. Okay, you can see from here from 1.3 to 0.6, but we can also see that also the shape of the bands changes, and in particular you see how some bands becomes very flat, and in particular this orbital here, so the bandwidth becomes very narrow. So it's in this range. It will not be surprising to find that this orbital localized in the mode sense. Okay, so let's now look. So we have so far looked how there are the interactions in each of these orbitals. So let's now look at how different so electrons in different orbitals interact. So what you can see here, so here we have first the intraorbital interactions here at 0, but also we know that we have several orbitals at this site. In particular, what we have found is that the two p orbitals, the two flat band orbitals, interact among so the intraorbital and the interorbital interactions are equal, okay? While the interaction is much smaller if we take into account, if we consider an orbital which is p with an orbital which is c. So here, so this is going to be important when we try to look at our system. And in general, what we see is that, well, for those electrons which are not in the same site, we see that the interactions decay more or less in a 1/r way, as it could be expected, like if we have, if the charge will be concentrated at each point, except for these two, which are very close and in fact are very extended. So this interaction in this sense is much more conventional than what it was found previously in this two orbital model. So it can be easier to think on that. So as I said, we think that so one will think that one can be more focused on these AAP orbitals. And in fact, we can see here how it's compared the interactions which are in this of this electron when they are in the same site or when they are in neighbor sites. So for those who write Hubbard models, this is telling us more or less how extended is the model. And in particular here, you can see that, well, this interaction goes, here is as a function of the twist angle. So you can see that this interaction goes like the inverse of the lattice constant, but this does not happen with the on-site interaction. In fact, the interaction of the electrons, which are here at the same site, it goes like the size, more like the size of the AA region. So it does not scale with the size of the Moiré. And the reason for this is that, well, so this twist bilayer graphene that we are studying is relaxed. So, so it's known that if the bilayer relaxes, so if the twist bilayer relaxes, the AA region stop following the size of the AA region, stop following the size of the Moiré, and tend to a constant value. So this is what we think it's observed here. So, but then what this is telling us is that so the interactions on site become more important as the twist angle is decreased. But in particular, you can see that the interaction between these electrons, which are in these sites, are not so large. Okay, so the ratio is relatively small. It's not as small as in other systems, but it's also not extremely large. Okay, so recently a new way of studying the phase diagram has been proposed. Well, has been studied, which is to control the distance or from a screening gate, from a metallic gate, and this way to control the interaction. And in particular, well, these are recent experiments by Dima Efetov, in which bringing closer the gate, he has managed to observe phase diagrams in which there is superconductivity without the correlated insulators. It has been also, there are in other experiments by Lee in US, so they can even put a bilayer graphene, bilayer graphene, and change the filling of this bilayer, and in this way control in situ the screen. So the question is, how are going to change the interactions in our system with the gate? So in general, well, so if we don't have any gate, we expect to have between the electrons a 1/r interaction. What we are assuming is that we are gating the system with a single gate. And so, well, we assume that this is through the image charges, and what you can see that the interaction is reduced. Now, the question is how close we have to bring our gate to affect these interactions among our electrons. So normally, people take as a reference the lattice constant. Now, you can see here how the on-site and how the first nearest neighbor interaction change with the distance to the gate. And in particular, you can see that if we put the gate at a distance equal to the Moiré unit cell, the on-site interaction has decreased only 11%. So somehow, if we want to have an influence of our system on interactions which are associated to the on-site energy, except we are very close to a transition, we probably would like to decrease it more. So to have an idea, if we want to decrease the interaction for about 30%, we should bring the gate to a distance which is of the order of 4 or 5 nanometers. On the other hand, with this interaction, even if here probably is not seen so much, it's reduced faster. In fact, at the screening length, at the Moiré constant, so it has decreased in a 40%. So somehow, so what we are doing here is mostly if with the if the distance to the gate is equal to the Moiré unit cell, the main effect here, it's been to just make our model less extended to just screen only the long range part. Okay, so before, so now that we know that how are the electron, how are the density interactions between our electrons, we have like already one term in our Hamiltonian. We can apply the simplest approximation that one can do, which is the Hartree approximation. And in this case, what one is doing is substituting the effect of the other electrons by an average potential, which depends on the occupation of the other electrons minus a reference. Well, in the literature, people have been using different references for these, different conventions for this reference. The one that we are using is we are canceling it here at the charge neutrality. And what you can see is that we are going to find a strong dependence of the bands with the filling. So this is system at charge neutrality. Here it's undoped, and we have here an angle of 1 degree. And now we dope with electrons. And now you can look at how these bonds. So you can see that these bonds have bended. So the gamma point, it's going downwards with respect to the K point, 2 electrons even more downwards, 3 electrons even more downwards. We dope with holes, so the opposite happens. It goes up. So here it's gamma with respect to K, larger change and even larger change. So this is the most clear relative shift that it happens, but it's not the only one. So in fact, there are shifts also. Sorry, there are changes also in the gap. You can see here that this band is here, the flat band becomes closer to these higher energy bands. And here they are even touching. And even smaller but fine changes happen here at this bandwidth, here at gamma, and also even there are small changes here in the bands, which are in the higher energy bands. So, of course, you have probably recognized that I was talking about the same effect that it was discussed in several talks last week. So these are, in fact, the results that Paco presented. And you can see that if you use the same value of the screening length, one can have, even once taking into account the difference in the bands, one gets a very similar magnitude. So look that this magnitude is quite high. Now, what is interesting from this result, in fact, is that we are getting this in a normal Hartree way in which this appears as a shift of the chemical potentials. In the model with 2 orbitals, with 2 Wannier orbitals per model, in fact, we have seen that to get this, one really have to go to very complex assisted hopping chains. So here in this model, it appears in a completely conventional way. And in fact, we can learn why this is happening. So we can go back now to our bands, okay? And you see that here, this Hartree correction, as I have said, this enters only, this enters as a shift, okay, but it's a shift which depends on the potential, depends on the orbital. So, and in fact, if you realize before, I have told you that at gamma, the kind of orbital that we had, it was different. So what this Hartree and this strong modification is revealing is precisely the presence of this other orbital weight at these flat bands. So, and then of course, so and the small changes that we have seen in the deformation here, I've seen before, sorry, these small changes are associated to the fact that also the orbital content at the upper band and the lower band is different. Now, another important aspect, which is it's interesting if we want to understand our system, is that when we have calculated this, we have taken into account the interaction between these orbitals and the other ones. If we haven't done this, this will have created a much larger potential. So this correction is first revealing the presence of the orbitals in this region here, and second, it's telling us that to take into account the interaction between them, it's going to be important in the properties. And let me now end with the other terms that we can find in our system. So we have so far seen the density terms, but of course in our system there can be other terms like exchange. Okay, so this is, for example, the Onsite Exchange is the typical Hund coupling. So we can see, well, if we want to calculate that, in particular, if we want to calculate that, we can calculate that in between the orbitals in the same valley or in different valleys. So for that, so we have to take into account how is the structure of the Wannier function. And in particular, we can see that these two exchanges, this Hund coupling, are going to be in both cases small. So in particular, in the case of the of the Hund coupling between different valleys, it's expected to be small because of changes in the atomic scale of the Wannier functions, different changes in different valleys. So somehow this will later give an integral to 0, while in this other case, this Hund coupling becomes very small due to some cancellation of the phases of this overlap function which changes at the Moiré scale. We find exchange terms of Hund coupling with other AAP or with other orbitals a bit larger, up to 3 milli-electron volts. This is not very large, and but in principle is comparable with the energies that people have seen so the difference in energies with respect to the when they look at different symmetry breaking state. However, in this case, we don't think these terms are going to be important because in fact the other states in general are far from the Fermi energy, and so we don't expect them to have much spin polarization. So probably all the exchange terms are not going to be important. And in the case of intersite exchange, we saw in the previous model for the Wannier functions that there were large changes, but in that case was because there were large overlaps between the functions. So in this case, here you can see the density of two of the orbitals. So if we consider here the AAP orbitals, so you see that, well, so these are well localized functions. And in fact, so when one of the functions reaches the other orbital, so we are here in this tail, and so this overlap is small. So in this case, the exchange again is also going to be small. Due to small overlap, and similar, this happens for assistant hopping terms. So then in general, if we only consider the interactions between electrons, which are centered here just between this AAP, only the density are important. There are some terms, some assisted hopping terms involving these orbitals and some here, so this D wave and these other ones, which are of the order up to 2 milli-electron volts. In principle, they seem smaller than any other quantities, but so it cannot be said that it will have absolutely zero effect. So let me summarize. So, and in fact, so the main thing is we have calculated these interactions in this model for Swiss bilayer graphene. So the main thing is the interactions in these models. So these are conventional density-density interactions. They are largest for the orbitals which dominate the flat bands, and the exchange and the assisted Hoping shapes are small. So in this sense, this model gives us a conventional, let's say, a bit complicated, but much more conventional model to study the correlation in these systems. We have also seen that if we want to screen the on-site interaction, we really have to bring the gate close. And also that we can really not forget about interactions or about the other orbitals, because already at the very simplest approximation, they have a strong, their presence in the flat bands have a strong effect. So the main thing is that we needed a convenient Hamiltonian to look, a convenient interacting Hamiltonian to look at the correlations in Swiss bilayer graphene, and now we have it. Thank you.
Thanks, Leni, for the very nice talk. I don't know if there are any questions. So far I don't see any. So I remind you that you can just raise your hand or directly type your question in Q&A, sorry, and then we'll take it. So I will just start with, it's a very naive question. So it's a bit far from my domain of expertise, but when you were mentioning this this distance effect that Dima has demonstrated, so the distance to the gate, I was wondering if there is any theoretical prediction for a structured gate. So during your talk, I was drawing this in my book. I don't know if you can see it, but it's like, maybe to make it clear, it's like if you have this this treated bilayer graphene, you were talking about this distance, but now if you have a structure system, would it be like a way somehow to generate a spatial correlation? So like to superimpose, let's say, a simpler symmetry of the Moiré. So you have the Moiré, and then you superimpose like, let's say, a very simple symmetry made by like 1D gates, like 1D fingers, that would somehow modulate the distance, because of course there is the vertical distance, but now you also have to take into account the, well, like, I don't know if I'm clear what I mean by this finger thing.
I think I understand what you are saying. Yeah, okay. In some way this will generate some periodic, some periodicity in the system. I think this is what you mean, some periodicity
exactly,
in the interactions. So the only thing is that probably it has to be really, really close, because so normally the main effect of a gate is going to be, well, the first effect of the gate is to cut the long range part of the interaction. So somehow it will, well, it will increase really, it will really create a system in which the interaction will change magnitudes and interaction range in a very interesting way, which I don't know is what exactly will appear, but yeah, it can be, if one really manages to get control with very, very close gates, it can give something interesting for sure, I think. Yeah.
Okay, well, thanks a lot, and let's go for some questions. So there is a question from Oscar Vafek. So wait a minute, Oscar. I'm putting you live. Up, Oscar. Yeah, so now you can speak. You had a question about ferromagnetism, right? Can you Can you speak now? Okay, so I will just ask for Oscar Vafek the question. His question is, how do you think about ferromagnetism in this formalism?
Well, so far we have just got the Hamiltonian. Now is the time to study that. But in principle, one can have different symmetry breakings in this state, in this system. So we haven't looked at the symmetry breaking yet. So this is what we should do now. Yeah.
Yeah. So I think I'm online now. It seems to me that the main players in this picture of yours is 2p orbitals on the AA sides. And they're Coulomb interacting. Are you not going to get more or less something like triangle lattice and the ferromagnetism type picture?
So well, here one thing is that I have, in principle, I have 4 orbitals in each side, so I can have different symmetry breakings. Because
there are 2 different valleys, right? But
yeah, well, valley, like different valleys, and also because I have two different p orbitals at each side, so I have different possibilities for breaking symmetries. But now, of course, one have also have to introduce the kinetic energy, which is and also, in fact, is what I have said. So our very well, the very first thing that I think it will show up here, I think mod physics will most probably appear. But now the question is to try to see how the effect of, first, the fact that our Hubbard model is not exactly Hubbard, it's a bit extended, and also which play, we have seen that even at the simplest level, the Hartree level, so this other orbital has shown up. So the very first way to think, if you just think this, the very first thing that you think is, okay, I just look at these AAP orbitals and I forget about anything else. But then what we have seen is that when we calculate this, if we don't include in some way the other orbitals, the effect is here, it will be almost double. So I think that now, so having in mind how small are going to be, so in principle, we don't have anything like a big exchange here, which is going to give us a clear symmetry breaking. So I think that one has to really look at the different scales with a bit of care. Yeah.
Right. So having the projected interaction directly onto the narrow band is that it very naturally gives you ferromagnetism, and it doesn't matter whether you do this in Wannier picture or whether you do it with Walk orbitals.
Well, ferromagnetism. No, it's what I say. So we may get this, but I still at this point I will not say anything clear, because, for example, also if I just have a Hubbard model in the triangular lattice, so I can also have some antiferromagnetism in kind of 120 degrees. It is not so most probably here experiment is telling us that this is not what is happening, but in principle, if I just have a Heisenberg, an antiferromagnetic Heisenberg model driven by super exchange, that could also appear. So I think that now one really have to introduce the different quantities. Yeah.
Okay, thanks a lot. I saw there were a question from Pablo and then suddenly disappeared. Maybe we'll come back in a moment. Let's move on from a question from Jose Pizarro. Jose, can you speak now? Okay, so I will read this question. This question is, do you expect any qualitative change when treating the screening in a more sophisticated way, such as in CRPA or in CFRG, or would it be only quantitative?
Well, for example, I think that, well, in fact, he has been doing the CRPA and all that, but what I imagine that if you do CRPA, the main thing it will be that when you do it, instead of just keeping the two flat bands, so just leaving the two flat bands, you just have to leave the eight bands. But in principle, my tendency it will be not to expect too many difference. But it's why I say we haven't done that. Yeah.
Okay. I see the next question is from Adrien Rousseau from Montpellier. Adrien, can you? I'm really sorry. I hope that it works. Well, I will ask his question.
Can you hear me?
Ah, yeah, now it works.
Okay, thank you. Thank you for this really nice talk. It's really far from my field. I'm not sure I will ask good question, but I'm just asking myself if this choice to use 8 wave function, Wannier wave function, is related to the number of atoms and the two same atoms in the unit cell, or can we use a same 8 wave function in the case of two different atoms like HBN?
I think this is also associated to the particular symmetry of this system. So in particular, for example, for the double twist bilayer, so the symmetry issues that I just mentioned before, they don't appear, and you work with conventional functions just with two orbitals. So this is associated with the symmetries which appear in twist bilayer.
And is it possible to extract this information of the number of wave function to use with a group theory analysis or something like this?
Well, in fact, the people who really built these the models did it starting from so considerations on the topology of the system and the symmetries of the systems. Yeah.
Okay.
Okay.
Thank you.
Thanks, Adrien. I see next question from Gang Lee. Gang, now you have the mic.
Hi, my question is for the 8 orbital model. Like, if we are only interested in the flat band, can we only include like 2 to 3 orbitals related to the flat band, and then the calculation can be very simple?
So well, this is what I mentioned at the beginning. So this is what people did when so in fact, so the first trials, or this is the way in which people still continue working with these models. So, but in fact, so people work with only 2 orbitals per valley. Now, what happens is that the Wannier functions that you obtain are very so they are very non-conventional, and they have these spinor functions that give a very complicated interactions. And so, in principle, so there is this model that people did for the two orbitals. So that was done at the beginning, but there are well, that it's a bit non-conventional. In fact, there is even some discussion on whether so the topology is seen, or so it's equal to the one that it should appear in the experiment or not.
Thank you.
Thanks a lot. I see there is one question from an anonymous that is asking, so I can't let that person speak because I don't have a contact. But the question is, does the weighting of each orbital to the band structure change after taking Hartree approximation into account?
We haven't checked that. I guess it should change slightly. Yeah. That it will not go to the sense, in the sense that one will still get, so you will not really realize on the difference on this.
Okay, well, that was it. Except if you have one more question, please ask it now. And if not, well, let's thank Leni again for this very nice talk. I just remind you also that all the talk are recorded and directly put on YouTube. And I just see like now they are already, some of them are already available on the YouTube account of ICFO. You have to look for ICFO in YouTube and you will find it. And so, well, thanks a lot, all of you for joining. Tomorrow we have 2 talks by Atachi Mamoglu and Rafael Fernandez. So hope you can make it. And now we zoom out now. And thanks all, and thanks Leni again for your talk.
Thank you very much. Thank you, Leni. Thank you, Antoine. And I'm gonna end this meeting, and I will see you at the post-topic session. Bye-bye.
Thanks, Al.